Let's look at combining elementary reactions. So an elementary reaction is a reaction that occurs in a single step. There's no intermediates. When we combine elementary reactions, we're making an overall reaction. And so we will see intermediates, most likely. So when we combine elementary reactions, say these two reactions shown here in step 1 and step 2, we're simply going to add the chemical equations together as if it was a mathematical equation. So we're going to sum up these two chemical equations. We're going to cancel out any species that show up on the product side of one reactant and the reactant side of another. And so, for instance, in this case, we have HI in the product side of the first reaction and HI in the reactant side of the second reaction, the first step and second step. Those are going to cancel. Nothing else in these chemical equations are going to cancel. So if we write the overall reaction, I'm going to write it below here in our question. We're going to have H2 gas plus 1,2 ICl gas forming I2 gas and 1,2 2HCl. And we can check to make sure that the equation is balanced. Let's see, we have two hydrogen, 2 chlorine, 2 chlorine, 2 iodine, 2 iodine. And so yes, the equation is balanced. We can also figure out the molecularity of each elementary step, so each step in the reaction. The molecularity refers to the number of molecules that must collide in order for the reaction to occur. Both of these are combine two reactants, so they are both bimolecular. We can also write the rate law for each elementary reaction. If we have elementary reactions, the rate laws can come directly from the reactants and their stoichiometry. So for instance, for step 1, we can write our rate law as rate equals K times the concentration of H2 raised to the power of 1, the stoichiometric coefficient, times ICl raised to the power of 1, again, those stoichiometric coefficients. For step 2, because this is an elementary reaction, we can write rate equals K times HI times ICl. Now, if we were to write the rate law for this mechanism, we would not simply be able to take the stoichiometry involved in the overall reaction and write a rate law from that. That only works for elementary reactions. A reaction where you're combining two or more steps is not an elementary reaction. So any intermediates, we already identified those. Those are something that shows up in the product side of one step and then the reactant side of another. So in this case, we have HI gas. We can take a look at a potential energy diagram for this reaction. So our reactants, we have H2 and 2 ICl. This is from our overall reaction. They react to form I2 and 2 HCl. So again, those are coming directly from the overall reaction, not from the elementary steps. We have some intermediates that show up. HI is a reaction intermediate. We've also formed HCl and ICl, but those, again, also show up as reactants and products. So our real reaction intermediate here is HI. Every time we have a step in a reaction mechanism, we have an activation energy, and we have a hill to climb. So for our first step, the activation energy will be given by the difference between the reactants and the top of the hill, the transition state. So we go over that hill to form the intermediates. We have a second step, which is also going to have another activation energy, shown here. The difference between the things that must combine, including the intermediate and the other reactants, to form the products. Because we see two peaks or two hills in our potential energy diagram, we know that we have a two-step process.